Alright, so now we're going to look at a projectile fired at an angle as opposed to some of the ones we've been doing which were fired horizontally. The big difference here is that when you fire it at an angle, V initial Y is no longer 0. In this particular problem, they give me the velocity and initial velocity at an angle alpha we fire from, and here's the given values: 37 meters per second at 53.1 degrees. That initial velocity is neither on the x or the y, as you can see. So the first thing we have to do is break into components v initial x and v initial y using just really SOHCAHTOA from what we went over in class. That immediately gives me their initial components on the x and on the y-axis. The x-axis component of the initial velocity, turns out it will be constant the whole way through the trip until it hits the ground or hits something, assuming there's no drag forces on it. This one will change throughout because it's on the axis of g. Alright, so we could do what we've been doing with horizontal problems, is list all my givens on the x-axis, list all my givens on the y-axis, and find its position as part A asks. There's really only one equation we got on the x because it's constant. So we pop in 22.2, which we got from over here, times at 2 seconds it's asking me about, and at 2 seconds we have a horizontal position of about 44.4 meters. And at the same time it's also moving vertically, so popping in our numbers from our givens up here into our y equation. This is the guy that works, we have 4 of them to pick from, and evaluating it, we're at 39.6 meters. So that should be pretty simple as long as you remember to break these two components up from that initial velocity. You could never plug this velocity into any of our equations over here because it's neither on the x nor on the y. We have to split that up. Okay, moving on, part A still also asks me to find the magnitude and direction of the velocity at 2 seconds. So using our givens from the other page and some knowns over here, remember I said that the horizontal velocity will remain the same the entire time. So we got out 22.2, so at 2 seconds it's still going to be going that horizontally. But because Vy is on the other axis affected by g, we're going to have to calculate it at 2 seconds. And we would just pick the first equation where Vy is equal to V initial y plus g times t. And V initial y, remember we got to as 29.6 meters per second plus 9.8 times 2.00. Evaluating those terms, we end up getting out 10 meters per second. 10.0 meters per second. Alright, so now that we have my x component and my y component, the overall velocity at 2 seconds is going to be equal to the resultant magnitude of those, 10 squared plus 22.2 squared. Throwing those values in and evaluating gives me a resultant of 24.3 meters per second. But it did also ask for direction, so we could even draw our little vector diagram here real quick to see what quadrant it comes out with. The x is positive, remember head to tail, so it's pointing this way. The y is also positive this way, and there's our resulting vector v at 2 seconds. What we could tell from this also is that at 2 seconds I'm on my way up. Since Vy came out a positive value and not a negative value, oops, missed a negative there, but that's still 10. Since that came out positive, we end up having, or knowing now, that we are definitely on the way up in the trajectory, not on the way down. So quickly evaluating angle phi, which I'll call it here, is the inverse tangent of 10 over 22.2. And the angle giving us the direction there is going to be 24.2 degrees. Alright, so not a whole lot different than what we've done. Just watch that initial velocity. Alright, part B goes on to ask me two things as well, and both of these things are about when it's at its peak. One thing to note, anytime we're dealing with its peak, is that the final velocity at that moment, if we froze it, is 0. It's kind of like when you throw a ball straight up and it comes straight down. For a moment before it changes that vertical direction, it has to freeze. So it first asks us to find t when this is happening, and we may still use v initial y is equal to 29.6 meters per second. We still know that g is equal to negative 9.8 on this axis at all times. And this time we can't use t equals 2 seconds because we're being asked for the time at this peak. So if we look over our knowns right here, it's actually the first equation in our list of kinematic equations, which would be Vy equals V initial y plus g times t. And this equation knows that if I plug in 0 right here, that only occurs in this trajectory at its peak. Therefore, t will equal negative v initial y over g. Plugging in those numbers, we're going to get negative 29.6 divided by negative 9.8. And the time we reach our peak at by evaluating that will be about 3.02 seconds. We have a second thing part B asks us as well, and that would be finding out what the max height is. So basically what we need to find from here to here is delta y at that moment. And knowing what we know, there's several different routes we could take. I'm going to try to use, like usual, only givens and knowns, which would be these three values here. But I will state in a moment how we could use the time at the peak to help us as well, if that would happen to be all we have. Alright, so anyways, delta y max occurs when we plug in 0. It knows, the formula will know that that's where we're at. So that's what our goal to get. And looking down over our equations, and with our givens and what we need to find, Vy squared equals V initial y squared plus 2 times g times delta y, and that will be my y max at its peak as long as I plug in 0 here. Alright, solving for that will yield this equation. And popping in our numbers will be negative 29.6 squared over 2 times negative 9.8. And therefore the peak looks like it will reach at 44.7 meters. Now we could have also, since we did figure out that time, at its peak, we could have also used the equation delta y equals v initial yt plus 1/2 gt squared, and that would have also got me 44.7 meters. Okay, and finally, this is a long problem. We're going to go on. We're going to go on and do part C, and that asks me a few things about the total trip. It says find the horizontal range. Range is a term now we're often going to use for delta x. So we need to find the horizontal range of the whole trip for when it comes back to the ground. And it looks like really that's all C's asking me for. So we just need to find this. Now to find it, we can use delta x equals Vx times t. If you recall, we do have Vx. We know it's 22.2 meters per second that we found found out right off the bat. But this time represents the time for the total trip. I'm drawing a little diagram again, just a real rough one. Here's a little thing we could do when we know that we came down to the same level ground in which we started. I need to figure out this t from here the whole way to here to figure out delta x as the range of the entire horizontal distance covered when it comes back down. How we're going to find that t with what we know is if I do come back down to the same level of which I fired it right here, that means vertically speaking my change in y, or my y displacement, actually equals 0. If I came back vertically to where I started, that's why that's going to be 0. So we could only do that noting a trip when I come back to the same level from which I threw it, kicked it, whatever, shot it, whatever way we fired this projectile. So knowing that, I'm going to go to this formula, because we still know that v initial y as well. And when I solve this for t, by plugging in 0 for delta y, that'll be the t of the whole trip, which I can then plug back in over here. Alright, so just running the algebra, now that we plugged in 0 here, we get divide out of t. And just have this single t, 0 divided by anything is 0. So this single t is what we have to solve for. So rearranging that formula is going to be negative initial y velocity times 2 over g. Plugging in my numbers, this is still going to be 29.6 meters per second that we found out originally over negative 9.8. Running those numbers, we've got a t of 6.04 seconds. And now that we have that, we may plug that in over here to answer what it asks, which is my horizontal range, using 22.2 as the x velocity and the time it takes for the whole entire trip, 6.04 seconds. Plugging those in will give us 134 meters that this ball covered. So that is a pretty typical problem. Oops, that should be an X. Where we find out features of a projectile. I can't draw an X today apparently. That's good enough for me. And that is in meters. There will be variations of this problem where sometimes we don't shoot it on a level surface where it ends up and stops up here. But this gives us the basics of what to do in a general scenario of something fired as a projectile.